This is Module 1 of the new Private Pesticide Applicator training. This module will be covering pesticides and basic principles of pest management. So, the first thing that you need to do for managing pests effectively is identifying the pest. Pests are undesirable living organisms that annoy, compete with, injure, or sicken people, crops, or livestock. So identifying the pest is always the first step for effective control. First, you want to establish the identity of the pest and determine whether it is potentially a threat to your crop. Some insects may be beneficial, so you don't want to eliminate those. Identifying the problem can be more difficult when the actual pest can't be found. You may have to identify the problem from crop injury or other signs of the pest, such as frass, webbing, eggs of insects, or leaf spots, blights, or decay. Understanding the life cycle or biology of the pest helps you understand when the pest may appear, what environmental conditions may make it more likely to appear, and when the pest is most susceptible to control. Farmers can get help with identifying their pests from their local extension offices, or many OSU extension publications are available for help. Don't guess on identifying the pests that you may have. So some pest management considerations are identifying whether this pest is really affecting your yields, because some injury may not be economically significant. A pest might even be beneficial. For example, beneficial insects should be left alone. If the pest is a known crop pest, it may be necessary or feasible to manage the pest with pesticides. Some questions to ask yourself when deciding whether to act are, is this stage of the pest controllable? Is the pest currently affecting yields? If not, at what level will the pest be expected to affect yield? Will the cost of control exceed the potential loss from the pest? So this gets us into pest action thresholds. Action thresholds are levels of a pest population that require some action to prevent losses. Thresholds may be based on economic, health, or aesthetic considerations. Farmers are concerned with economic thresholds, which is the point where the cost of the potential loss begins to exceed the cost of treatment. The action threshold is the level of a pest population where you must take action to prevent the economic loss. Action thresholds have been established for some crops and pests to help guide management considerations. Outside of agriculture, there may be quite different action thresholds. For example, where human health is threatened by a pest, the action threshold may be very low or zero. Zero would mean that there is no level of pest activity tolerable. So pest management goals are related to the action thresholds. As mentioned previously, you may have zero tolerance for a pest that is a serious health threat. The goal here is to eradicate or completely eliminate that pest. In agriculture, suppression and prevention are two of the most common pest management goals because it's rarely possible or cost-effective to completely eradicate the pest. In the next slide, we'll see an example of a threshold for a disease with an action threshold of 10% for a foliar disease. In this example, a certain amount of disease is tolerated, that is 10%, before action is taken. So the goal here is suppression of the disease. With very devastating pests, experience may show that very heavy economic losses occur from any amount of infestation. Here you would use preventative strategies where the farmer wagers that the potential losses from the pest are greater than the control cost and makes an application of a pesticide before or at the first sign of a pest. An important consideration with fungicides is that as a group they perform much better when applied preventatively compared to curatively which is after the disease onset. So for many diseases, preventative control is the only good option. Overall, a farmer must rely on his knowledge of the past history and weather conditions and cultural conditions that stimulate a disease and make a preventative application when experience suggests it is likely to occur. So here we have an example of a pest management threshold. This is an example of using a visual rating based on the amount of disease observed per leaf. In this example, the 10% threshold is what we see here in the red box. As stated before, fungicides have either no or limited curative capability, so action thresholds for a disease may be very low. So it's very important to monitor pests and weather conditions to make management decisions. Scouting for pests on a regular basis will help determine what pests are present, if an action threshold has been met, and whether any action is needed. OSU Extension publishes information about thresholds for key crop pests. In addition, you may know your field history and if it has a history of a certain pest, so you can likely predict that you're going to get the same pest again. This is why keeping good records can be very helpful. Scouting is also important after a pesticide application to determine whether it was effective. It's also the only way to determine whether your pest may be resistant to the pesticide you're using. Traps, as seen in this picture, are available for some types of pests. Others you may have to actively scout the field. Monitoring the local weather conditions is also important for predicting pest problems and for making decisions about application timing. Many disease pathogens are highly dependent on weather conditions, and some may need to be treated preventatively if the weather conditions are conducive to the disease. In contrast, mite populations tend to peak under hot and dry weather conditions. So your knowledge of the past history of pest infestations, when they occurred and under what conditions, will help you stay informed about management decisions. Over time, keeping good pest management records and assessing the effectiveness of each pest management action will help you make the best decisions, control pests effectively, and avoid unnecessary treatments. So a popular term that you may have heard about is called integrated pest management. This is using a combination of appropriate strategies to reduce pests to an acceptable level while minimizing harm to non-target organisms and the environment. IPM strategies almost always include cultural controls. Cultural control entails altering the environment so it's less favorable to the pest. This may include crop rotation, manipulating planting date, using trap crops, removing crop residues, among other things. Biological control involves using a natural predator to control pests. Mechanical or physical control uses devices or physical barriers to manage or exclude pests. Examples are cultivation for weeds, cultivation crop traps, and screens. Chemical control or the use of pesticides and herbicides should be used in a combination with these other tactics. The first step, as we talked about in the beginning of this presentation for IPM, is to always properly identify the pest. So to go over some common pest control failures, one of the most common is a failure to identify the pest correctly. Some may want to try to save money and use a lower dose of pesticides rather than the labeled rate. This is not only going to leave you with ineffective control, but also contributes to pesticide resistance. Timing is also very important when dealing with pests. For example, if you miss the vulnerable stage of the pest, such as when they're actively feeding, you may have a wasted application. Another scenario in which it may appear that you've achieved poor control is that you in fact did not control the pest population, but another pest infestation has been moved in, or the same pest came back. It's also possible that the pest you're trying to control has developed resistance to the pesticide you are using. As previously stated, it's very important to scout fields after an application to detect any resistance. So let's go over this topic of resistance and how it develops. Pesticide resistance occurs in a pest population, meaning one species, when a normally lethal dose of a pesticide no longer controls that pest. We're going to go over to see an example of how pesticide resistance develops when you're using the same mode of action or group of pesticides repeatedly in the same field. So here's a visual to show how resistance naturally arises in a pest population from time to time. The green plants represent the normal population that is susceptible to the pesticide. From time to time, by natural genetic mechanisms, an individual that is resistant to the pesticide or the pesticide mode of action appears in the pest population, and that is depicted by the red plants here. So, to show what occurs when the same pesticides or a group of related chemistries with the same mode of action is used repeatedly, the normal, non-resistant type of pest, the green plant, is killed off. However, the resistant types, the red, have found a way to overcome the effects of the pesticide. Therefore, the resistant pests will thrive and multiply because you've killed off all of the competition, which is the non-resistant types. So this gets us into talking about the mode of action, or the MOA. The mode of action is the way that the pesticide kills the pest. MOA of some pesticides is highly specific, often affecting a single site or step in a complex biochemical pathway. Resistance develops most easily when a single site is affected by the pesticide class. Related chemicals with similar structures often have the same mode of action. Chemical manufacturers now indicate the resistance or mode of action group by group number on the pesticide label, as you can see circled here. This pesticide indicates that it has two modes of action because it's a premix of two herbicides with the mode of action groups 14 and 15. So now back to our resistance example. Here this shows that using a single mode of action over more time enables the resistant pest to take over the field. A pesticide that once worked well now has little or no effect. Versus a way to manage resistance is when using chemical controls is to avoid using the same chemical class repeatedly. If you had previously switched to an alternative chemistry with an alternative mode of action, you would manage this pest and have no survivors. The goal of resistance management with a pesticide is to leave no survivors to develop resistance. Practically speaking, complete eradication may not be feasible, but when you're battling resistance, getting as close as possible to eliminating the pest is the goal. Leaving no survivors does not mean that we use pesticides excessively to nuke everything in the field. Rather, it means we use pesticides according to the label and as effectively as possible to prevent resistant populations from gaining the upper hand. Of course, using a pesticide and alternating modes of action is only one possible management tool, including non-chemical means of managing the pest. Like we talked about earlier, practicing IPM strategies is critical to managing resistance. So Just to summarize, in order to minimize pesticide resistance, farmers can alternate chemistries by alternating pesticides with the different group numbers. And in addition to this, rotating the classes of the chemistry, more than one chemical class can be tank mixed to achieve the same results as alternating pesticides. Another way to manage resistance includes treating the pest at the most susceptible stage. For example, treating weeds before they exceed the size limitation on the label. Also using full labeled rates and utilizing IPM, which would be using other methods of control and not relying solely on chemical pesticides. One common problem is treating too late, when the pest has reached a size or stage where it is more or less immune to the pesticide. This is a common mistake farmers make in their battle with resistant weeds in Ohio. When battling a resistant pest, be sure to scout the fields after the application to see if it was effective. If not, promptly follow up with the pesticide with a different mode of action or use effective non-chemical methods to control the pest. Here, this label indicates that it is a tank mixture of pesticides from two modes of action, herbicide mode of action groups 14 and 15. So why is it important to manage resistance? Simply, if we don't manage resistance, we'll run out of options to control the pest. In order to keep the pesticide arsenal viable and to avoid creating super races of pests, we must practice pesticide resistance management. Now we're going to talk about pesticide formulations. It's important to understand what we mean by the pesticide formulation and what the distinctions are between different kinds of formulations. A pesticide formulation includes everything that makes up the product. The active ingredient is the toxic material that kills or controls the pest and is always listed on the pesticide label as percent by weight. The inert or non-active ingredients listed as other in this example are the parts of the formulation that have important functions but do not have to be listed on the label. Examples of non-active ingredients include the carrier and adjuvants. The carrier is what the active ingredient is diluted with and can be a liquid or dry material. A single active ingredient can be formulated as different products with different carriers. For example, you can have the same AI in both liquid and dry formulations. Adjuvants or additives are inert ingredients that enhance the physical or chemical properties of a formulation and make the active ingredient more effective. Common examples of formulations for dry include wettable powders, a finely ground powder, and dispersible granules, WG or WDG, a somewhat larger size dry material. Both of these formulations are insoluble and when mixed with water, make a suspension that must be agitated to keep the product suspended in water. Granular and dust formulations are dry formulations that are not mixed with water. They are applied with dry application equipment. Granular and dust formulations are both ready-to-use formulations, and this designation is abbreviated as RTU. Liquid formulations, some common ones are emulsifiable concentrates, which have oil-soluble active ingredients that are formulated with a petroleum-based solvent. A special type of adjuvant called an emulsifier allows the oil-soluble formulation to mix with water, forming a milky white suspension of droplets. Agitation is less important with ECs than wettable powders and wettable granules. EC formulations provide superior penetration of leaves, which is especially important with weed control, but also may be absorbed through skin more readily than WPs and WGs. Solutions are liquid formulations in solution and where the active ingredient is completely dissolved in the carrier. Flowables, F, are liquid suspensions of insoluble active ingredients. Even though it is a liquid formulation, in the tank they behave like a wettable powder or wettable granule. Agitation with these is very important. A couple more miscellaneous common formulations are baits, which are a food substance combined with a pesticide. They attract the pest and kill the pest when it consumes the food. Also, water-soluble packet formulations, which when you open the container, you see small packets. They're designed to be placed directly in the tank, not opening the packets. The packaging protects the user from exposure. The packet will actually dissolve in water and release the pesticide. So, as we just stated, water-soluble packets, abbreviated WSP, are the most common types of formulation. Don't open the packets, and as this is against the label and defeats their preventative purpose. This packaging is water soluble, and they're meant to be added directly to the tank. So in pesticide formulations, one active ingredient can be available in multiple formulations. For example, the same active ingredient might be available in granular wettable powder and emulsifiable concentrate formulations. The type of formulation is an important consideration for the applicator. One formulation can be more acutely toxic than another, requiring additional personal protection equipment. Primary exposure route of concern is likely to be different between different formulations as well. For example, wettable powders have an inhalation concern, while the emulsifiable concentrate formulations have a greater dermal exposure hazard. ECs have greater dermal exposure hazard than liquid flowables because oil-soluble material are able to penetrate the skin more readily. After toxicity, there are quite a few practical considerations related to pesticide formulations. Equipment may be needed for different formulations. The formulation also affects physical properties such as the tank mix. Constant tank agitation is required for formulations that form suspensions with wettable powders, wettable granules, and flowables, because these formulations will settle at the bottom of the tank without agitation. Formulation chemistry also affects tank mix compatibility and tank mix order. Consult the label carefully when mixing multiple pesticides or perform a compatibility test prior to tank mixing. Incompatible pesticides will not mix, and the result may be clogged hoses and tank residues that are difficult to remove. Tank mix order refers to the order in which you add different types of formulations to the tank. Always follow the label's recommendations. Mixing in the proper order affects the compatibility of the tank mix. So we've mentioned adjuvants. A tank adjuvant is a broad term describing any additive to a spray tank that enhances pesticide activity and/or the physical properties of the spray mixture. Adjuvants are designed to perform specific functions, including buffering, dispersing, emulsifying, spreading, sticking, and wetting. Adjuvants can also reduce evaporation, foaming, spray drift, and volatilization. Surfactants are surface active ingredients, also called wetting agents and spreaders, that change the physical properties of the water droplets. Adjuvants themselves have no pesticidal properties, therefore they are not required to be registered by the EPA. Before using any adjuvant, you should check the pesticide's label. As we said with surfactants, These have surface active agents. So they change the property of the water droplet by lowering the surface tension. For example, with a wetting agent, one type of surfactant, the droplet spreads better over the overall surface of the leaf. Addition of the wetting agent improves control by increasing the spray coverage and uptake into the leaf. Penetrants and crop oils help pesticides move into the leaf. A buffering agent maintains an optimal pH range in the spray tank. Anti-foaming agents prevent the tank mix from foaming, and compatibility agents prevent physical or chemical incompatibility. So that's the end of this module. There is a quiz contained in the online course for Module 1, as well as the quiz questions in the core study guide on pages 40 to 45.